Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Today, we are going to look at an interesting concept under mechanics, which is going to be basically dealing with the concept of rigid bodies. Now, in this case, we are going to, of course, try and contrast this specific aspect of the concept of bodies, particularly using the Cartesian coordinate system, which we have done in one way or another in some of our videos. Now, in this case, I'm going to use a series of illustrations. And of course, we are going to see that basically from the definition, we are going to get a sense of particularly what this aspect of the rigid body entail. Now, later on, we shall look at the concept of degrees of freedom, which are going to assist us appreciate the various range of degrees of freedom which are going to be associated with the concept of course, what we refer to as rigid bodies. Now, we're going also to look at a number of, particularly two types of motion which are going to be associated with the concept of rigid bodies. And at the end, of course, of our discussion today, we're going to look also at some of the conservation, or rather some of the treatments which we are going to be associating with the rigid bodies, especially in trying to evaluate the type of forces which are going to be involved in this case. Now, therefore, we shall look at the concept of this specific definition of what we refer to as a rigid body. Now, in this case, I'm going to give this one in a summary form in order for us to be moving at a relatively, of course, a faster way. Or in a sense, in case I need to borrow from some of the videos which we have discussed, I will just be mentioning those general concepts which I feel are, of course, relevant for us. Now, in this case, a rigid body is going to be a body that is going to, of course, exhibit a tendency of not deforming or changing shape. And of course, we're going to also to see that this specific aspect of a body that does not deform. So I'm going to have this one in a summary form, but I'm going to elaborate on this specific aspect of the statements, basically, which I'm not going to be giving in details, but in a summary form. So a rigid body is basically a body that does not deform or change shape. Now, in our previous videos, we have said that the interaction of forces and surfaces, or entirely the concept of a body, are going to be particularly affecting those bodies in a way that they can either deform or change shape. Now, we're going to see that basically in the concept of motion of these specific rigid bodies, they are not going to show some kind of deformation or changing of their shapes. And that's one way in which we can, of course, try to refer this aspect of a rigid body. And some other cases, we're going to see that apart from this specific, of course, review of a rigid body, we are going to define this specific concept of a rigid body as a collection of particles. This a rigid body is a collection of particles which perhaps we can give in terms of properties. So this collection of particles are going to have a property in a sense that if this particular rigid body is going to be, of course, changing position, then therefore in the course of motion, this collection of particles are going to maintain their specific position, whereby if I give it in terms of particularly a quick illustration, we're going to see that if this body is considered to be a rigid body and is changing its position from A to B, and therefore, if this particular body constitutes of a various range of particles, which are going to be given perhaps in terms of this specific illustration. So let's consider this one to be, particularly I can use different notation. So in case we consider this one as a particle, perhaps let's have this one as particle 1 and then particle 2. So upon motion or changing the position, we're going to see that this is going to be still the position of particle 1 and 2 given as that one. And of course, we're going to see that for us to have meaning from this specific definition, then therefore this body is going to be a collection of particles. But we're going to see that this particular particles or body is going to have a property such that the distance between the particles are going to remain unchanged in this specific course of motion. So therefore, if we consider this specific distance between particle 1 and 2 given as such, so let's have this specific distance given as d. Now, at a change from the position of this specific particle from A to B, we are still going to have this specific distance between A and B maintained as such, and therefore that's going to give us a meaning in the second definition, which is a formally defined way of a collection of particles with the property that the distance between the particles are going to remain unchanged, and this is going to be realized within the course of a motion of this specific aspect of a rigid body. Now, therefore, from topic of discussion for today, which we have defined the concept of a rigid body, it's going to be the dynamics of a rigid body. Now, the concept of a dynamics of a rigid body is going to be dealing with the motion of these rigid bodies. And in this motion of rigid bodies, there are some of the laws which we are going to be considering, which are going to assist us in trying to come with a various range of formula, which are going to assist us in trying to, of course, appreciate this specific treatment of these rigid bodies. And among these specific formula which we are going to look at, I'm going to mention three. And the first one is the principle of what we refer to as a linear momentum. And in this case, as I said, I'm going to mention some of these specific aspects which we are going to consider to be relevant for us. And in this case, the principle of linear momentum is going to be dealing with the aspects of a force and a mass. And of course, we're going to see that the position vector is also going to be playing a vital role if we're going to consider the motion of such a kind of bodies which we have referred to as rigid bodies. Now, therefore, this principle is going to dictate that if we have the first derivative of the product of mass and the position vector given as r, this is going to be giving us the product of a mass. And so if we use this specific symbol for this one, this is going to refer to as the first derivative with respect to time. And if I use this specific symbol, then therefore this is going to refer to the second derivative with respect to time as such. So if you have a position vector given in terms of r, and we have a second derivative, and therefore this is going to be giving us the concept of acceleration. So in this case, we are going to have this principle of linear momentum given in terms of this particular formula, whereby we're going to have this one equivalent to the concept of force. Now, in this case, we're going to see that this particular force is going to be given using this specific formula. And in this case, of course, I've mentioned that we're going to regard this one as the total mass, which is going to be the mass under consideration. And then we shall have this specific concept of r as a position vector. So this is going to be a position vector which I've particularly mentioned, and of course which is going to be a position a vector of the center of mass of this particular rigid body with respect to the origin. And of course, in this case, if I mention the concept of origin, I'm going to refer to the Cartesian coordinate system, which I've of course mentioned in our introductory part of our discussion. So I'm going to be creating, of course, more elaboration on this specific case. But from this case, this is going to be a position vector, which is going to be, of course, a position vector of the center of mass of the rigid body with respect to the origin. Now, and then we are going to have this aspect of a force, which is going to be basically the aspect of the net external force, which we are going to consider against this specific rigid body. And these are going to form basically the summary of the principle of linear momentum, which we are going to consider in dynamics of rigid bodies. Now, then we're going to also look at the principle of angular momentum, which is going to be assisting us, of course, in trying to evaluate what we refer to as the moment of inertia of these particular rigid bodies with respect to the center of mass. And of course, we're also going to look at the concept of angular velocity and the aspect of torque. So therefore, the principle of angular momentum is going to provide for us this specific relationship, which we are going to have it given in terms of this is going to be referred to as a torque, or sometimes we're going to use this one as the total moment of the forces about the center of mass. And this is going to be given as the first derivative of this specific product of the moment of inertia about that center of mass given as such, and omega. So in this case, omega is going to be referring to the angular velocity. And of course, the total of this one can be given in terms of, so we're going to see that this is going to be a constant, and therefore we are going to do this derivation with respect to angular velocity. So this is going to give us this of course moment of inertia given as such of the initial or the moment of inertia of this rigid body about the center of mass, and we're going to have the first derivative of angular of course velocity, which is going to be given in terms of that. So this is going to be summing up our aspect of the concept of the principle of angular momentum, and this is going to be associating assisting us trying to of course find out these specific characteristics of the of course a rigid body which I've mentioned. Then lastly, we're going to look at another concept which of course is going to be dealing with the principle of conservation of energy. So this is the principle of conservation of energy, which also is going to play a vital role in trying to assist us understand, describe the dynamics of a rigid body. So in this case, this is going to be considering the conservative, of course, forces. And if we consider these external forces, which I've mentioned, of course, to be a conservative, and our last discussion, I mentioned the concept of conservative forces, which are going to be disregarding the path taken by this specific, of course, object under consideration. And of course, we're going to consider its initial and final state in that particular case. And that's going to be giving us the concept of conservative forces. So if we consider these external forces to be conservative, we're going to see that the potential energy of this particular rigid body can be given using this specific relationship. Now, in our last discussion, I had mentioned that this is going to be the kinetic energy plus the potential energy are going to be giving us the sum of the total energy, which is going to be a mechanical energy of that specific system. Now, we can use this specific illustration whereby we're going to use this position vector, which is going to be the first derivative implying velocity. Now, from our previous discussion, we have said that the kinetic energy can be given in terms of half v squared, and therefore this is going to be representing our t in this case, and then we shall have this specific, of course, aspect of the potential energy given in terms of a half. And this we mentioned was basically this aspect of the moment of inertia for a rigid body about the center of mass given as I subscript c, and this is going to be given as the square of omega given as that one, and then we shall have plus v. So in this case, the first and the second aspect are going to be the translational and rotational aspect of kinetic energy, which we are going to derive in our subsequent videos. And then we shall have the kinetic energy, the potential energy given as that one. And this is going to be equivalent to the total energy of this specific system, which is going to be constant. So these are some of the laws which we are going to consider in our dynamics of rigid bodies. And I'd like to invite our members for the second discussion, which is going to form our final bit of this specific introduction to the dynamics of rigid bodies. And this is going to create for us a basis in trying to understand basically what these dynamics of rigid bodies entail. And of course, as I had said from my previous discussion, I'm not going to close this discussion without mentioning that concept of the degrees of freedom, which are going to assist us appreciate the various types of motion which are going to be displayed by rigid bodies. Now, unlike particles, as we're going to see, the concept of rigid bodies are going to display 6 degrees of freedom, whereby the particles are going to be displaying 3 degrees of freedom in that particular case. So I'm going to use particularly the 3-coordinate system, or the 3 Cartesian coordinate, 3-dimensional Cartesian coordinate system in trying to illustrate this one. So we're going to have this one as x-axis, the y-axis, and z-axis. But if we consider a particle that is going to translate along this particular axis, then we're going to have the x translation, which basically implies that a particle can either translate in the positive x or negative x direction given as such. And then we're going to have a y translation, which means a particle can translate either in the positive y or negative y direction. And that's also going to be the case for the z, of course, axis given as such. So therefore, we are also going to have a translation of a positive or negative z direction given as such. So in this case, these are going to constitute 3 degrees of freedom of these specific particles. So this is going to be 3 degrees of freedom. But we're going to see that if we consider a rigid body, so this is going to be, regard this one as a particle. So in case we consider a rigid body, I'm going to give an example of an aeroplane. So perhaps I can give this rough sketch for a plane given as such. I hope my, of course, illustration is going to be uh, elaborate. So we're going to have this one given as such, whereby we shall have the wings of this plane given as such. So if we consider this plane to be, of course, situated at this specific position, and therefore we have this specific axis which is going to cut across the horizontal position from this one, and then we shall have a vertical one which is going to be pointing downwards. So in case we consider another one towards this specific position, we're going to consider this one to be mutually perpendicular to one another. So in this case, this as well can point the other opposite direction, but I've decided to put it in for the sake of our space so that we can appreciate that particular orientation. So we're going to consider the motion of this specific plane within that specific point which I've given, which is an intersection of those axes. So in the case we have this vertical position or axis which is going to be given at that one. So if the plane moves in this specific direction within that course, then we're going to refer to that one as a yaw, or a yawing of the plane within that specific axis. So if the plane moves its specific, of course, wings in a vertical direction, in a sense that it's going to be moving in a rolling position, then therefore we are going to refer to that one as rolling motion. But we can as well consider this one, if the plane moves its nose in the up and down direction, then therefore that's going to be referred to as the concept of a pitching. So in this case, we are also going to have the concept of a pitching. So we can consider this plane as a rigid body, which is going to be displaying other, of course, aspects of motion apart from the first three which we have mentioned, which are going to constitute rolling, yawing, and pitching, which are going to be additional degrees of freedom. So we're going to see that this specific case, if we consider the plane to be a rigid body, then therefore apart from the 3 degrees of position along the axis, we're also going to have additional ones which are going to be experienced from a single point given as such. So therefore we are going to consider a rigid body to be having 6 degrees of freedom, which are going to be the translational motion which are going to be experienced along this Cartesian 3-dimensional Cartesian coordinate system, and the 3 which are going to be of course experienced from a single point, whereby they are going to constitute the roll, yaw, and the pitch axis given as such. So kindly check our description boxes for various links of other similar videos. Subscribe and engage us in the comment section, and also ring that notification bell to be getting updates from our previous or our various discussion which we have done under the concept of a mechanism. Now in our next discussion, as I said, we're going to look at an extension of this specific part, and of course it's going to create for us an emphasis or an additional information on how we can describe the motion of our rigid bodies. So that is it for now, guys. By God bless you. Catch us in our next video.